Hello and welcome everyone to the Varsity Tutors StarCourse series, where it has been a pretty wild summer weather season already. We've had heat waves in the Pacific Northwest. We've had monsoons in the Southwest. We've had thunderstorms and lightning, and the hurricane season is just starting to get heated up. We've got wildfires. Fortunately, if you want to know why it's happening, what you can do about it, and how to appreciate the beauty of nature from a safe distance, we have the perfect teacher here for you today. Reed Timmer, a storm chaser. You may remember him from all kinds of other Varsity Tutors classes, is going to tell us all about why this wild summer weather is happening and continuing to happen. And again, what you should know about it, both as just a person who may experience it and as a future storm chaser. We also have a team of future storm chasers with us here. We've got our Weather Wonders campers. Weather Wonders campers, where's everybody at here? Who's excited for class? Awesome. We got the Weather Wonders campers here. If you're interested in joining Weather Wonders campers, we're going to have a link up on the screen for you here. But if today whets your appetite and you get excited about learning more and more about weather, Varsity Tutors has you covered. We're actually going to lead me to two things for you guys to know before I turn it over to Reed to get us started. One, make sure you've got a camera nearby. In about 35 minutes, we're going to give everybody a chance to lean into the screen and take a selfie with Reed. If you do that and upload it to Instagram, you'll be entered to win a spot in Weather Wonders Camp or Weather Wonders Club as we get into the school year and kind of switch formats and timings and everything. Also, make sure you see the chat box to the right of the screen here. It's going to say ask on it. You can actually ask and answer questions in that spot throughout today's class. So Reed's going to ask you a bunch of questions to find out what kind of weather you've experienced, what you know about weather, and what kind of weather you really appreciate and love seeing. And so use that area there to answer those questions. And if you have any questions whatsoever for Reed in the last 10 minutes of class, we're going to get all of your questions answered about weather. So drop your questions in that ask area there, and I'll interview Reed with your questions in just a little bit. But with all of that said, it is time to turn it over to your teacher for today, professional storm chaser, and the guy who knows more about what's happening around us than anyone, Reed Timmer.
Thank you, everybody, for joining me for this wild summer weather class. We are going to be covering a lot of different types of summer weather. Many of you know me just from chasing tornadoes, usually during the spring and summer. Tornadoes do happen during the summer months as well, but there's a lot of other types of extreme weather to chase during the summer. That includes the monsoon storms in the southwestern U.S., those big storms and flash floods and debris flows. I actually just got back after about 10 days of chasing those flash floods in the desert Southwest. There is not much more that's more powerful than those debris flows that come off of those wildfire burn scars. And we do have many active wildfires across the western U.S. as well. The Dixie Fire has grown very large to number 2 officially, or even the largest non-complex fire so far in California. And I know there are many that have joined from Illinois. That yesterday there was a big tornado outbreak as well across northern Illinois, some damage that was caused up there as well. Those storms that are riding over top those big summertime high pressure areas. And one common theme you're going to see throughout this course is during the summer months, that's when temperatures get the hottest. That's when that jet stream or that river of air, stronger air in the mid and upper levels of the atmosphere, lifts way to the north up into Canada. That's why most of the tornadoes and severe weather this time of year usually happens across the Canadian prairies and also to the northeast of the Great Lakes there across Ontario as well. Sometimes that severe weather does come south into the northern U.S. and the Corn Belt, like we saw those tornadoes across northern Illinois yesterday. But also hurricane season is about to come alive in a big way. And we're going to be talking about tropical cyclones big time during at least half of this course. We have Tropical Cyclone Fred that might be named in the coming days. That one's forming out as a tropical depression right now, deep out into the tropical Atlantic. But this time of year, late in the summer into the early fall, that's the prime time for those tropical cyclones. As the jet stream lifts off to the north, you have a reduction of wind shear to the south of that jet stream. Massive, sprawling subtropical high pressures will take over. And usually when you hear about the word high pressure, you associate that with nice weather, clear skies, dry conditions, heat waves even. But sometimes these high pressures can also cause an influx of moisture and storms, like with monsoon season off to the western edge of that monsoon. You'll get that influx of moisture off to the north. The Bermuda High out in the open Atlantic definitely dictates where those tropical cyclones will travel. And there you can see that jet stream. That's the river of air aloft, that fast moving air up in the mid and upper levels of the atmosphere. And for those that have joined our earlier courses on tornadoes and supercell storms, you know that those tornadoes and monster mothership supercells that we talk about during the spring and summer, those thrive off of the wind shear that the jet streams provide. So those stronger winds aloft, that helps those supercells organize. But summertime storms like tropical cyclones and hurricanes are different. They don't like wind shear. So if that jet stream is further south, they can act to tear those storms apart. And hurricanes are those giant heat engines in our planet that will transport heat from the warm ocean surface to aloft in the atmosphere. They thrive off of environments with relatively minimal wind shear or environments with high pressure aloft. And that allows those giant heat engines to be more vertically oriented and to continue transporting heat aloft into the atmosphere. And that massive ridge out in the open Atlantic that you can see on this image, that's the Bermuda High. That's one of those big subtropical high pressure areas that we talk about that dominate summer climate. But that is also very important on directing hurricanes from east to west down into the tropics, and also could determine whether they curve to the north and can even miss North America completely if that Bermuda High is a little bit off to the east. And you can, of course, see the monsoon there in the southwestern US on the western edge of that big summertime high pressure that often dominates the mountain west and can lead to those wildfires. The southerly flow on the western side of that anticyclone that are spinning clockwise in a clockwise direction, that pumps moisture up from the eastern tropical Pacific Ocean. And that's what fuels those big monsoonal storms that we see in the desert Southwest, those massive dust storms, and the big flash floods that are so dangerous out there this time of year. So now we're going to start with a question here before we dive deeper into tropical cyclones, hurricanes, and typhoons. Here's a big question for you. What is the difference between a typhoon and a hurricane? And I'm already starting to see some great answers flooding in. And believe it or not, it's actually not a different type of a storm, even though they have different names. Certain parts of the planet will call tropical cyclones or stronger tropical cyclones with wind speeds of 74 miles an hour or greater. Sometimes they'll call them other names. So on the Eastern Hemisphere, out on the other side of the Western Pacific Ocean, hurricanes are simply called typhoons over there. And then when you get a really strong hurricane, like a Category 4 or Category 5 storm in the Western Tropical Pacific, it's called a super typhoon. So those are some of the strongest storms anywhere on the planet. The strongest tropical cyclones tend to happen in the tropical Western Pacific, where the water temperatures are extremely warm out there. The environment is very prime for tropical cyclones to intensify. Not a lot of wind shear out in the Western Tropical Pacific this time of year as well. And that leads to the formation of those massive super typhoons. But we also get very powerful hurricanes in the Atlantic basin too. And that satellite image that I'm playing here, that high resolution satellite image, that is Category 5 Hurricane Dorian that happened in 2019 on approach to Marsh Harbor there in the Bahamas. And this storm was heading straight for the Florida coastline, the east coast of Florida. People were lined up and down the east coast of Florida. Everybody was evacuating. And thankfully, very powerful Category 5 Hurricane Dorian put on the brakes to the east of Florida. But very unfortunately for the Bahamas, it put on the brakes right over the northern Bahama Islands there and just ravaged the islands with Category 5 conditions, storm surges well in excess of 10 to 15 feet out there, and winds gusting well over 200 miles an hour. And with an EF5 tornado, that's usually the wind speeds that you'll get with an EF5 are greater than 200 miles an hour. But with a massive Category 5 hurricane like this, the eye is 10 miles across. It's like a tornado that's about 5 times larger, but within that eye wall, it is capable of producing wind speeds equally as strong. But tropical cyclones are actually giant heat engines in our planet, and they're measured by 2 different ways. One is the wind speed, with the tropical depressions having winds of less than 39 miles an hour. As they gradually intensify and the pressure starts to lower inside the storm, that drives stronger and stronger winds at the center of that storm. And once it gets above 39 miles an hour, that's when they become tropical storms. That's when they're named. That's when we might see Tropical Storm Fred out in the open Atlantic. These are also associated with certain pressure levels too. Pressure can be more easily measured in the center of the hurricane by hurricane hunter aircraft as well. So the lower that pressure falls in the center of the hurricane, generally, the more the intense the storm. And then when those winds get greater, and these are maximum sustained winds, 1 minute average winds that determine the rating of these hurricanes from category 1 to category 5. That's called the Saffir-Simpson scale of hurricane intensity, starting off with a category 1 storm. That's the weakest of the storms, but still capable of life-threatening impacts and very powerful winds. Maximum sustained winds of 80, 90 miles an hour is different than a gust, because those gusts can go much higher, even up into the triple digits, gusting above 100 miles an hour, which is very capable of producing damage. But you get category 3 or higher on the Saffir-Simpson scale, and that's called a major hurricane. That's when you're starting to get those winds that are comparable to that of a tornado and even a strong tornado. And then you get the catastrophic hurricane that is a category 5. That is the worst of the worst, the strongest hurricane, strongest heat engine anywhere on the planet. The most recent category 5 to impact the United States was Hurricane Michael, and that was back in 2018. That was actually a hurricane that I chased with my little dog Gizmo there, and that definitely produced winds gusting well over 200 miles an hour and a very dangerous storm surge. And we're going to dig a lot deeper into the impacts of these hurricanes and the structure of hurricanes as well coming up, and their role as the giant heat engines on our planet from the tropics up to the poles. And now I want to talk about the typical life cycle of a hurricane. Right now, we've got Tropical Depression 6 that's out in the tropical Atlantic right now. There's a lot of forecast models, or those spaghetti plots that will show the track of that storm, many of them showing east to west on the southern periphery of that Bermuda High. Usually those hurricanes will begin as a tropical wave. And these are easterly waves, so they're different than the trough of low pressure in the jet stream that is now lifted up to Canada. Those troughs will move west to east. Those are called Rossby waves. They thrive off of the temperature gradients that are currently up in Canada. But to the south of that jet stream, where everything is warm, and then way down to the south into the tropics, you get what are called easterly waves. A lot of times they'll start with a monsoon type of a pattern in West Africa. That's an uptick in thunderstorms out there in Western Africa. And those complexes of storms, or mesoscale convective systems, will migrate out over the warm waters of the tropical Atlantic, initially as a tropical wave moving east to west. It'll almost look like a boomerang there, moving east to west. And as it feeds off of that warm water at the ocean surface, it starts to get more and more blobs of convection, or storms. We call that convection. And that's the process of transporting heat from those very warm ocean temperatures. Generally speaking, if the sea surface temperatures are greater than 80 degrees Fahrenheit, then a tropical cyclone will continue to intensify and feed off of that heat energy at the ocean surface. If it drops below 80 degrees, then they will start to weaken. And if the hurricane moves off of that warm ocean surface and over land, then they will quickly deteriorate. But once you start to get those storms conglomerating and forming into a blob, then it starts releasing heat. As you get runaway condensation, water vapor turning into clouds, turning into rain, it releases heat that's stored inside the water molecules called latent heat. And that's a huge part of the heat transport on our planet this time of year. And a big part of that heat transport is made possible by these tropical cyclones, the big blobs of storms that you see in the center of them. And those storms will continue to release that heat, leading to surface pressure falls near the ocean surface. That low pressure will continue to fall. That causes wind to converge in toward that low pressure, and it has nowhere to go but up. So that enhances the updraft. That converging air right at the ocean surface leads to the formation of more storms. We call this a positive feedback, when that cycle gets out of control and continues to feed off of each other. Once that storm gets a closed rotation, then it's called a tropical depression. And as that positive feedback continues to intensify the storm, those winds will increase above 39 miles an hour. Then you get a tropical storm. And then once they get 74 miles an hour and greater, that's when you get a hurricane. And the more and more surface pressure falls that you get, the more intense those storms develop. It causes sinking motion in the center of the storm, right in the middle. And that allows the formation of the clear eye that can happen. And that stadium effect that we talk about within the most powerful hurricanes, that's when you get a perfectly clear eye, storms rotating all around you, and you get what it looks like when you're inside of a stadium looking straight up. You see the clear blue sky above, and then the wall of those storms all the way around you, just releasing all that latent heat energy, transporting it from the ocean surface aloft and from the tropics up toward the poles. And a big impact of these hurricanes, it's not just the wind. Even though the Saffir-Simpson scale is based on wind speed and wind damage, the stronger those winds and the stronger the tropical cyclone, you also get one of the most devastating and impactful parts of a hurricane impact, and that is the storm surge, or the piling up of ocean water as these storms approach the coastline. And there are two different mechanisms for causing this ocean level rise when a hurricane is coming in. You can see the graphic at the bottom right, that area within the concave portion of northwestern Florida. A hurricane rotates anti-clockwise. Against clockwise, it's basically a cyclone, goes against the opposite direction that an anticyclone or high pressure goes. So on the east side of a hurricane, in the northern hemisphere at least, you get southerly winds. On the west side of the hurricane, you get very strong northerly winds. So as a hurricane is approaching the coastline from south to north, the right side of that storm has very strong southerly winds piling up that ocean water against the coastline. The coastline is basically a barrier for that water. So the wind just keeps piling up that water. You can see in the video there from Hurricane Sally last year near the Gulf Shores area, that storm surge just starts to get going and you get those little waves upon wave upon wave. And it's actually on top of the tidal level. So if it occurs during high tide, the water level inundation on the land areas is even more substantial. And the other mechanism is when that low pressure happens right in the center of the hurricane, you have much less weight of the atmosphere above that center low pressure area. And that causes just a little bubble in the ocean to rise up. And that little bubble also can be an ocean rise. And that can lead to that greatest storm surge wrapping all the way in toward the center of the hurricane. You don't only get just the piling up of the water, that causes about 70 to 80% of the storm surge, but also those really powerful hurricanes with very low pressure and not a lot of weight of air above it can also lead to a little bit of an ocean rise. But there you can see all of that powerful southerly winds. This is actually Hurricane Zeta, a video from down at the very tip of Louisiana, Venice, Louisiana, right near the mouth of the Mississippi River. That's an area that's incredibly prone to these storm surges. And one thing we're doing as storm chasers is laying out a network of storm surge sensors called surginators that can measure the depth of storm surge inundation in real time. And now I want to talk a little bit more about the nuts and bolts of tropical cyclones, and especially the role of tropical cyclones as those heat engines. And this is a bit of a summary of everything that we've covered so far. Basically, tropical cyclones and hurricanes exist on the order of about 500 kilometers or larger. They're very large storms, different than tornadoes or supercell storms that occur on the order of tens of kilometers. Tornadoes a lot smaller than that, on the order of about 1 kilometer. So these massive storms have massive thunderstorms associated with them, and that is pivotal for latent heat release. Those thunderstorms will lead to rapid condensation, and every water molecule, the water that we drink, has energy stored within the bonds of those molecules. And when you get a phase change from water vapor, which is in the air, it's invisible. When that condenses and you get cloud matter, heavy rainfall, that releases heat midway up in the atmosphere inside the storm. And so as these storms thrive and feed off of the ocean heat temperatures, they are transporting heat from the surface aloft in the atmosphere and from the equator to the poles. And all of that is because the Earth is heated unequally at the equatorial regions to the mid-latitudes. And also the summer, which is a part of the seasonal cycle that is the warmest in both hemispheres, that causes the polar front jet stream to lift dramatically to the north and allows all of this wild summer weather to happen just south of it. But the structure of these hurricanes as well, you have the eye wall in the very center of that storm. That's where a majority of those very powerful storms are located. And this shows you the structure of those hurricanes. And I also include looking straight down at the storm from a satellite image at the left, but also a cross section at the right. And this is to encourage you to think of the atmosphere as a layer cake. Think of it in 3 dimensions. Not only are you looking down at these storms from space, which basically makes them look like a painting or a picture, but they exist in 3D. They have vertical development as well. And the cross section at right really shows their role as a heat engine as well. Those arrows pointing straight upward, that shows the transport of heat from the warm ocean surface to aloft. You can see the eye wall as well. That's a donut-shaped ring of very intense storms that encapsulates the eye. So the very strongest storms, you'll get sinking motion right in the middle of the storm, right in the inside of that donut of very intense storms. So those storms are associated with big time updrafts and the strongest winds produced anywhere in the hurricane. When we talk about those maximum sustained winds of 150 miles an hour, that's a 1 minute average wind speed that is usually found right in the middle of the eye wall. And that's because the pressure gradient is greatest there. That low pressure right at the center of the storm, the pressure increases as you go out. And so the tighter the pressure gradient, the stronger the winds are ripping around that. And that happens inside the eye wall of the storm. And that's also where the greatest heat transport happens. The greatest latent heat release happens in the center of those big time storms. And you can see at the top, you get what's called upper level outflow. Those are usually cirrus clouds that are rotating the opposite direction as the hurricane. They'll be rotating clockwise. Basically, it creates its own high pressure up above it. And that's that heat getting dissipated aloft in the upper atmosphere. That completes the transport from the warm ocean surface to aloft in the atmosphere. And you also get many outer spiral bands too. When a hurricane is rotating, it has an inner core. Those are the most intense storms, basically a continuous donut of storms, including the eye wall and a little bit further out of the eye wall. But then you get outside of the inner core, which is a larger donut, and you'll get some dry air that will wrap into the hurricane as well. You can get spiral bands of thunderstorms that will wrap around. And those spiral bands are also capable of producing tornadoes. You can get little supercell storms within those spiral bands that can produce waterspouts, and also waterspouts that will come ashore as damaging tornadoes. But even those outer bands, the thunderstorms in there, also play a big role in transporting heat from the very warm ocean surface to aloft inside the lower atmosphere. But you can also see the vertically oriented hurricane there. If you were to impose wind shear on that, if the jet stream were to start to interact with that hurricane, then it'll start getting a tilt. Instead of being this perfectly vertically oriented, efficient heat engine, maximum efficiency at transporting that heat from the warm ocean surface greater than 80 degrees to aloft, once that jet stream starts to sag a little bit further south, starts to interact with the tropical cyclone, it causes it to tilt. And then it can begin the transition away from a tropical cyclone and more toward an extratropical cyclone, or those big time mid-latitude cyclones like a nor'easter in the northeastern US. And sometimes, like on the east coast of North America, you can see that warm ocean current, that pink arrow that goes from south to north up the east side of the coast. That's called the Gulf Stream. And that's a warm ocean current that is transporting that warm tropical and subtropical water northward. So it is possible for a tropical cyclone to maintain its tropical characteristics much further and longer further north if it's able to parallel that Gulf Stream. But overall, with tropical cyclone climatology, tropical cyclones love warm water. And in fact, surface temperatures that are less than 80 degrees Fahrenheit, and then the storm slowly starts to dissipate, slowly starts to lose its intensity, losing its energy, which is really the heat energy of the ocean. And that's why the cold ocean current that's along the West Coast, I know we have some Weather Wonders campers that are from Oregon. You know that the ocean temperature is extremely cool out there when you swim in the Pacific Ocean that far north. That's because there's a cold ocean current, the California current on the West Coast, that brings that cold water from the Gulf of Alaska southward. And hurricanes don't like that cold water. And that's why you very rarely, basically never, will have a hurricane landfall in California or further north than that because of those cold ocean currents. The opposite is true, though, in the western tropical Pacific Ocean. That's where the strongest tropical cyclones anywhere in the world typically happen. And that's because the ocean temperatures are warmer out there. You get an abundance of storms as well. You can see those two red bands, west to east bands down in the tropics that are denoted with the dashed line. That is the intertropical convergence zone, or the ITCZ. And there's two of those usually. They get active this time of year in the fall in the northern hemisphere, and in the fall in the southern hemisphere, which is actually our spring. Everything is flip-flop from the northern hemisphere to the southern hemisphere. But this time of year, the intertropical convergence zone sets up a little bit further north in the subtropical belt there, north of the equator, in the tropical Atlantic, and throughout the tropical Pacific. And that's where you get those easterly waves, those tropical waves that'll move from east to west along with the trade winds. And one interlocking theme that we'll see throughout this class is the importance of these massive sprawling summertime high pressure areas, or anticyclones. And those are denoted there by the blue H. And the wind generally circulates clockwise around anticyclones in the northern hemisphere. And those are very important for steering these massive heat engines, hurricanes and typhoons. Usually they'll wrap around the southern side where you get those east to west winds. And then if that high pressure is compact enough, the southerly winds on the west side of it can act to steer those hurricanes northward toward the poles. Another thing that can cause a hurricane to steer is when that polar front jet stream can drop a little bit south, or if you get a trough within that jet stream, that can cause a hurricane to turn northward right in front of it as well. And there are other different steering mechanisms that many of the meteorologists and forecast models take into account when we're trying to forecast a very complicated forecast track with these tropical cyclones and hurricanes. And now I want to talk about some of the strongest tropical cyclones ever recorded. This one stands out especially to me. In 2005, I was in grad school at the University of Oklahoma studying meteorology, and we were all just watching in awe as this hurricane rapidly intensified in one night. Basically went from a tropical depression, tropical storm into one of the strongest hurricanes ever to be recorded in the Atlantic Basin, and definitely in terms of the pressure fall. The pressure was estimated at 882 millibars, the central minimum pressure inside that hurricane. And look at that satellite image. You can see that little dot right in the center of the storm. That is called the dreaded pinhole eye. Very compact, very small. When you see a very compact, clear eye like that, you know that the eye wall is very tight and compact around that eye as well. And those winds are rapidly changing directions in there, constantly changing directions, constantly accelerating. And those winds were gusting well over 200 miles an hour, probably pushing 250 miles an hour there in gusts in the middle of that hurricane. And that eye was only 2 miles across. And the crazy thing is that I've actually chased tornadoes that are bigger in diameter than the pinhole eye at the center of Hurricane Wilma, which is one of the strongest tropical cyclones to ever be recorded in the tropical Atlantic. The tornado that happened in El Reno, Oklahoma in 2013 was actually 2.5 miles wide, as the widest tornado to ever be recorded in history. And the pinhole eye of Hurricane Wilma was actually smaller in diameter than that. So if you can imagine being on a boat, which you would not want to be near that pinhole eye because the waves would be so insane and the winds would be so strong, but you could actually see condensation or a wedge-like tornado probably all the way down to the ocean surface inside the eye wall that is Hurricane Wilma. And arguably out in the typhoon zone, Super Typhoon Tip back in 1979 had the lowest ever recorded central pressure inside a tropical cyclone, an astounding 870 millibars. So if you can imagine the pressure gradient on the outside of that low pressure at the center of that storm, big time winds out there in the Western tropical Pacific with super typhoons like Typhoon Tip. Now, just a summary, want to reiterate how important hurricanes and typhoons and really any tropical cyclone or any blob of storms or convection in the tropics, it's very important and plays a vital role in the heat transport in our planet from the tropics and the subtropics to the poles, from the warm ocean surface to aloft in the atmosphere. I really think that that's their purpose on this planet, is to transport heat. And all of that is because of what's called latent heat. That's the heat energy that's stored within the water molecules. And when you get a phase change from water vapor in the air, which is invisible, nestled within the air that I'm here at Team Dominator headquarters, that water vapor, as it changes into cloud matter or liquid water droplets or rainfall within those intense storms, especially inside the eye wall of very intense hurricanes and super typhoons, that leads to rapid heat transport. And those positive feedbacks, those cycles that we see in summertime weather, whether you're talking about tropical cyclones or drought, heat domes, even the monsoon, those positive feedbacks are very important as well, because they lead to the ramping up of these giant heat engines in barotropic environments, which are basically environments with a reduction of wind shear. As the jet stream lifts north up into Canada, you get these environments with very little wind shear that allow hurricanes and typhoons to thrive. Now we're going to pivot and shift gears. That's one thing that is unique about summer, is you get a wide variety of different types of wild storms. You don't only get the tropical cyclones, hurricanes, and typhoons. You also get tornadoes that'll rip, we call those ridge runners, those disturbances that go over top those big summertime anticyclones. We had that yesterday with a tornado outbreak. We get a lot of derechos as well that we could see today, portions of southern Wisconsin into northern Illinois. We also get the wildfires out west as well. But one of the personal favorites that I enjoy to chase are the monsoon in the southwestern US. And that's a seasonal shift in the wind direction that causes an uptick in storms and moisture. And some of the monsoons and other tropical locations like West Africa or India are a lot more powerful. And watch this video on the bottom right. I just intercepted that about a week or two ago. Very powerful. That right there is a debris flow. That's a flash flood off of a wildfire burn scar during monsoon season. This video here is a nighttime flash flood that I intercepted in southern Utah with an absolute flood chasing expert. David Rankin grew up there in southern Utah, chasing down these flash floods with big time debris. And a lot of times these flash floods in the desert Southwest, where you usually get dry conditions, they have what's called a debris plug on the front edge. There you can see the debris, sticks in there, boulders. I flew my drone to be able to see those above, and you can see that debris plug there in Escalante, Utah. You notice how the color of those flash floods are brown, red, even a chalky color. The first one that I showed you was jet black, and that came from a burn scar, a wildfire, the Pine Gulch fire burn scar north of Grand Junction, Colorado last year. All those big time wildfires that were burning across Colorado and are currently burning in California. When the monsoon develops in the southwestern US and you get that seasonal shift, the southerly winds bring that moisture northward from the tropical Atlantic, you start getting these storms that will sometimes develop over these burn scars. And when they drop rain over an hour period, just in excess of about 1/2 of an inch, all of that rain drops on the burn scar. All the vegetation is burned away, just leaving that mud and debris to get picked up by the runoff. And all of that debris flows into those dry creeks and canyons, gradually accumulating water behind it. Then it'll develop that debris plug on the front edge, which is the trees, the rocks, the debris there. That moves a little bit slower because it's interacting with the friction of the earth, and it allows all the water to pile up back behind it. And then it comes through very dramatic, like you saw in that video. And that flash flood, I actually could hear it from about 2 to 3 miles away. So I knew it was a substantial flash flood. I flew my drone to assess just how big it is, just to know that I can safely cover that flash flood. But that's one thing. Even though these wildfires in California happened last year, 1 year later with an energized monsoon, we're still dealing with those impacts with these dangerous debris flows and flash floods that are flowing off of those massive burn scars. And here is that seasonal shift that we talk about. In order to be called a monsoon, some people, if there's a big storm happening outside, will just call that a monsoon, but that's actually not a monsoon. It's part of a larger scale circulation that is a monsoon, basically a seasonal shift in wind direction. The rest of the year outside of the late summer, the desert Southwest is extremely dry. You hardly get any precipitation out there. The spadefoot toads are well underneath the ground, hibernating until the next rainfall comes. But then in the late summer, you get the development of that massive subtropical high, those big sprawling high pressure areas that will dominate the central US, that will wobble around a little bit. On the western side of that high pressure, which is rotating in a clockwise direction, you get those southerly winds pumping that moisture northward from the eastern tropical Pacific. And that leads to very intense thunderstorms to develop in these desert climates. What you see at the bottom left is a massive dust storm. Some call them haboobs as well. There are even dust storm warnings that are issued out there in Arizona and across the southwestern US. And that's actually a giant storm that produces so much rain that it hits the ground and spreads out. It's basically a big squall line or a shelf cloud, and it picks up all the loose dust on the ground. So those first storms that you get when the monsoon first fires up earlier in the summer can cause these massive walls of dust or dust storms. And those are even capable of lofting little things like baby scorpions, baby spiders, little fungus as well, a suspended fungus within the dust cloud. So if you actually get hit by that haboob and breathe in that air, you can actually get sick with something called valley fever, which is where you get the fungus, some of the bacteria, little things that are picked up off the desert floor. And if you inhale, it can even be toxic. But it definitely is intense, shooting these massive walls of dust called dust storms. That is definitely an impact of monsoon, very multifaceted impacts during the monsoon season. You get those dust storms, you get flash floods, you get crazy lightning in locations that are beautiful, like the Grand Canyon as well. But if you're a hiker or a camper and you're in the desert Southwest and your family is going into a slot canyon, this time of year, you got to pay extreme focus on the weather forecast and that flash flood potential, because sometimes those flash floods can go into those slot canyons and fill up the entire canyon with water and debris. So that's why a better time of year to explore the desert, especially those slot canyons, is outside of monsoon season, the early spring, usually during the winter as well. Still important though to stay tuned to those weather forecasts, because the monsoon, even though it is beautiful, can also be very dangerous. And another part that is also associated with those massive summertime high pressure areas that take over to the south of the jet stream as it migrates up into Canada. When all my Canadian friends are chasing tornadoes up in the central US, a lot of times down in the mountain west, beneath or on the periphery of those big time anticyclones, you get massive wildfires. And this is something that's getting a lot worse over recent years as well. You have fires that are regularly growing in size to up over 400,000 acres. Out in California, for example, we had many fires out here in Colorado that grew to much larger than 100 and 200,000 acres as well. The East Troublesome Fire, Cameron Peak Fire, the Pine Gulch Fire, where that big flash flood that I showed you just a little bit ago, that actually came off of the Pine Gulch Fire to the north of Grand Junction. So anytime you get the development of these big subtropical anticyclones, they're associated with dry air, low relative humidity, and the periphery of those anticyclones, you also get very strong winds as well. One a pattern out in California that's incredibly dangerous for these wildfires are called Santa Ana winds. And that's kind of a squeeze play between those very large subtropical summertime high pressure areas and a thermal low as well. Sometimes cutoff lows will form in the Eastern Pacific. And that squeeze play, the pressure gradient will accelerate those winds. And the worst fire conditions you can get are ones that are very low relative humidity with strong winds. That can lead to very aggressive wildfire behavior. Sometimes the most active and hot fires will lead to the development of a storm-like cloud, almost like a cumulonimbus cloud called a pyrocumulus. You can see one here. This was taken by my friend of the East Troublesome Fire in Colorado. That was the one that caused so much damage there around Grand Lake, just outside of the Granby area. And that wildfire was unprecedented because it actually crossed the Continental Divide. So the Continental Divide is an area of the highest terrain there in the central US. And it's unprecedented for that continent, for a wildfire to actually move across the Continental Divide. The highest peaks are located there, 14ers, or those peaks that are above 14,000 feet. But this fire was so substantial that it actually crossed the Continental Divide and was threatening Estes Park last fall. But that is a textbook example of a pyrocumulus cloud. See how it has that almost like a nuclear almost looks like a nuclear blast, like a cumulonimbus cloud or a supercell storm. That's because the fire is so hot, it leads to a dramatic updraft. And eventually it cools to the dew point and you get condensation as well, cloud matter. Pyrocumulus clouds can even produce lightning. They can turn into thunderstorms, and that lightning at the periphery of that pyrocumulus can start new fires, can promote wildfire expansion as well. And when you get wind shear with that pyrocumulus, it leads to almost like a supercell effect. And these can start to rotate and develop mesocyclones. When that updraft starts to spin, then it's called a mesocyclone. And there have even been cases when that rotating pyrocumulus produces a damaging tornado or a fire whirl that is located right at the edge of that temperature gradient. And those fire whirls can even migrate away from the fire and cause damage away from the burn zones. I've actually seen damage caused by a strong fire whirl out in Redding, California from the Carr Fire. It caused tornado-like damage that wasn't burnt. It was away from the burn zone. And it's just fascinating that these pyrocumulus storms can become so intense that when you superimpose wind shear, get a little bit stronger wind aloft, maybe the jet stream comes back south, that will cause these things to tilt and also start to rotate. And that's when you start to get fire NATO potential, or those fire whirls, which are just an incredibly dangerous and powerful phenomenon to witness. And as I mentioned, wildfires are getting worse, larger, more frequent as well. This time series shows from about 1980, pretty close to present. And in fact, it doesn't show the last couple of years in which it's even ramped up even more. And in fact, the 8 largest fires in California history all happened within the last 4 years. So that's pretty scary. It just seems like every single summer and fall, we're getting bigger fires, bigger pyrocumulus clouds. And I was talking to some of my storm chaser friends, and we were saying that the next EF5 tornado to happen is probably going to be associated with a pyrocumulus cloud and actually not a traditional mesocyclone. So you'll see these things form on radar. They ramp up, start to spin, produce firenadoes. But wildfires are definitely getting worse with time. That's related to global warming. Certainly, you're getting these massive heat domes. You're getting bigger drought, long-term heat waves, bigger fires. And it's also related to forest management, the fuels that are available for those fires to burn. But when you're getting warmer, drier conditions, windier conditions that are lasting throughout the year, we're not only getting wildfires at late summer into early fall, but they're extending all the way through the year. You're getting wildfires even in the winter in some cases. They're starting in the early spring out in California. And that's definitely a scary thought that those wildfires could just continue to get worse with climate change. And these wildfires will often happen in the middle of long-term heat waves and droughts. And there is a difference between a short-term heat dome and a long-term heat wave and drought. But what causes those are those positive feedbacks or those cycles that are built in to this wild summer weather. And those positive feedbacks, like what we saw with the hurricanes, with the runaway heat release, the lower pressure falls, the greater convergence, more storms, more heat release, stronger storm that allows those to intensify into Category 5 hurricanes or super typhoons. A similar cycle, positive feedback also happens with the development of these big time droughts and heat waves. So when a big heat dome develops like this, you can see that high pressure area causes a jet stream to bulge way up to the north. That was actually the recent heat dome in the Pacific Northwest. It happened earlier this summer with unprecedented temperatures, even above 110 degrees out there. That's because it's called an anticyclone wave breaking event. The jet stream lifts so far north that it becomes unstable. You get a cutoff anticyclone, and that heat dome will just sit there and spin and produce hot, dry conditions day after day, continuing to warm as well. But that leads to drier vegetation. You get a drying out of the land surface. You get less moisture down there as well. That leads to hotter temperatures, greater feedbacks within. And eventually, sometimes these heat domes that may last for just a couple of days can actually trigger a longer term drought because the built-in positive feedbacks, the drier, less vegetation, less cloud cover, less moisture, less clouds as well, more sun coming in, hotter temperatures. It can actually cause the development of these large ridges and lead to greater persistence of these summertime ridges. And so sometimes these heat domes can actually lead to longer term drought. The most recent really severe drought was around 2012. Finally came to an end just after that, about 2013, and I think especially 2015. But that was a recent, very long-term drought. And now it looks like we're in the beginning of another long-term drought. And a lot of these droughts also depend on what we call teleconnections. Sea surface temperature patterns like El Nino and La Nina in the tropical Pacific certainly do play a role. Sea surface temperatures in the North Pacific as well can play a role in the development of these heat domes. You also have the background condition of global warming. And there is a lot of debate. Would that heat dome in the Pacific Northwest have happened if we didn't have global warming? Many leading scientists are arguing that. It definitely was made worse by global warming. That background warming that we have that's more gradual and longer term definitely could have played a role in those positive feedbacks that are so inherent in global warming with the development of that heat dome as part of this longer term drought across the Western US. But interestingly, drought is a very complex phenomenon. It's very locally specific as well. For example, the Western US, the desert, the Rocky Mountains, much of that land is not as efficient at absorbing rainfall. You get a lot of runoff out there in the Western US as well, whereas the clay type soils, the sandy loams further east, those are much better at storing water within its pores. So a very different rainfall amounts or different conditions will qualify for drought depending on the geology and the geography of the area as well. But right now you can see the drought monitor, which is released every week. That also factors in those local conditions like soil type, runoff, mean climate. We are getting dominated by a big time drought across the Western US, and that extends across the northern plains as well. There's even been wildfires in areas like Western Nebraska so far, Banner County so far this year, and that drought is causing the development of these wildfires where we otherwise wouldn't see them. But it does look like we'll at least have a couple of years of drought. Those positive feedbacks are at work. We're getting stronger anticyclones, bigger anticyclones during the summer months. And hopefully here in a couple of years, we'll get the opposite and start to get a pluvial, which is a condition where you get an abundance of rainfall. And it does seem like we're getting a lot more droughts and heat waves these days with the changing climate than we are the opposite. So this is just a summary of our class so far here on wild summer weather. It's very dependent on these massive anticyclones, really all of this wide variety of crazy weather that we see during the summer, from the monsoon storms to the haboobs to the wildfires out west, to the heat domes, to the hurricanes and tropical cyclones in the intertropical convergence zone, like upcoming tropical cyclone Fred that might threaten the eastern Gulf of Mexico and possibly even the southeastern US. All of those are directly or indirectly dependent on these massive anticyclones that will develop to the south of the jet stream, and also the migration of the jet stream, which thrives off of the temperature gradients, or baroclinic environments, we call that, the opposite of barotropic. When that jet stream lifts up to Canada, it opens the door for this wild summer weather to happen to the south of it within the barotropic environment, those storms that will feed off of a reduced amount of wind shear in the deep layers of the atmosphere.
Hey, Reed, thank you. I don't know about everybody else. I'm inspired and excited, but exhausted. Man. There's a lot of weather that happens in the summer. So thank you for such an amazing tour of what happens and why it happens. We've got time now. We're going to go a little overtime for questions, but we mentioned at the beginning, we want everybody to grab a camera. Now is really the time to do that. So if you guys grab a camera, kind of get yourselves lined up. We're going to go full screen to Reed here in just a second to get everybody those pictures. Remember, if you upload it to Instagram, tag Reed TIMMER and tag Varsity Tutors, you'll be entered to win a spot in Wild Weather. Not Wild Weather, the Weather Wonders Camp. There's some normal weather too, or Weather Wonders Club coming up this fall. There's going to be a link on your screen in a second to be able to learn a little bit more in case you just want to register, in case you don't win. But hopefully everybody's got their cameras here. Reed, I'm going to turn it back full screen to you, and let's make sure everybody gets those pictures.
Thank you, everybody. Great photos. Never stop chasing.
All right, perfect. And then now hopefully everybody got those pictures. We'll put Reed full screen a couple times while he's answering questions here. You guys have had some pretty amazing ones. One, I just want to do a quick synopsis of kind of what I took away from today, Reed. Just make sure we're kind of on this, because we covered a lot of ground. But really what it comes down to, like you said toward the end, is the jet stream rises. We get different pressure system that brings in those anticyclones, and really all of these kind of weather phenomenon, they take on different personalities, I guess, based on where they're located. If you're near water, water's a big part of it. If you're not, then maybe drought and high heat are a part of it. But it sounds like it's all fairly well related. Do we have that right?
That's right. And all of it involves the heat transport in our planet too, with a lot of heat happening in the equatorial regions and the tropics, and a lot less heat happening at the poles. And you need to be able to transport that heat from the equatorial regions to the poles, and from the ocean surface to aloft. And that's a big role of these tropical cyclones, these massive storms that happen, hurricanes, typhoons across the globe, and also the monsoon too. That's all about transport of heat and moisture, usually from south to north, and also the thunderstorms within those monsoons and the complexes of storms also play a huge role in heat transport as well. And the importance of those positive feedbacks, or the cycles that feed off each other with summer weather, are so important. And those are the same themes that drive global warming as well across the globe on much longer time scales than the extreme weather that we've just been discussing.
Yeah, thank you for that. That idea of the positive feedback loops is fascinating, right? We saw it with the pyrocumulus clouds, and they can cause lightning, which causes more fire and all those kind of things. We see it with the spiral of the hurricane. It picks up more wind, more storms, and keeps continuing to build. So it's fascinating how the weather works, and we appreciate you sharing all this with us. Now we got some questions from everyone out there. We got some questions from the live studio audience. I think Christian from Weather Wonders Camp had a question for you, so we're getting him up on screen here. Christian, you got a question for Reed?
Yes.
Hi, Christian. How are you?
Hi. The
Yeah,
question
fire
I
away.
have, why do flash floods have dirt and other kinds of stuff?
That's a good question. Flash floods will pick up anything in their path, and as they grow and evolve as well. Usually the flash floods in the western US and those desert locations will have a lot greater debris. And a lot of times the first flash flood of the year also has a lot of debris. So usually the thunderstorm that will produce those flash floods can be a little bit further away than where the flash flood is observed, maybe over a mountain, up above a canyon as well. The storms can feed off of those mountains, and they'll dump the rain up in the forested area of the mountains. Maybe it's a wildfire burn scar where a lot of that vegetation is burnt away, just exposing that debris, the sticks, the dirt, the rocks to be picked up by that water. And so the water starts falling, and once it hits the ground, it starts to undergo runoff. It flows downhill, wants to flow into those creeks and canyons. But when you get really rapid rainfall falling, then it also picks up debris, sticks, rocks, dirt, picks it up, especially those burn scars where there's no vegetation to hold that soil and debris in place. And then eventually it reaches the creek bottom, bringing all that debris down with it. And it starts to accumulate a pile of debris at the front edge of the flood. And that's interacting with the friction of the earth, basically the rough ground, the rocks, the rounded rocks there at the bottom of the creek bed. So it's moving a little bit slower than the water back behind it. And that debris keeps accumulating, growing bigger and bigger at the front wall of the flood, called a debris plug. Sometimes you can get massive sticks and boulders in the biggest floods. And then behind it, you get the rushing water that catches up behind it and actually builds that debris plug bigger and bigger, almost like a positive feedback mechanism in itself.
Nice. Thank you for that. That's it is pretty wild. Those videos you showed of those debris flows were absolutely wild. So fascinated to know where they came from. Hey, speaking of the origin of certain things, one of my favorite ones was where do hurricanes and typhoons or really tropical cyclones, where do they start? We talked a lot about how they get going, the feedback loops and all those, and kind of that they like warm water. But how do they get started? Are there particular origins? I thought that was a great question. So what do you have for us on that?
Well, they can actually start as a blob of thunderstorms, oftentimes in monsoon conditions in other parts of the globe, like West Africa, the West African Sahel region. It's called basically a vast grassland in Western Africa. They also experience a monsoon, even more substantial than the monsoon that we see in the desert southwestern US, a big seasonal shift of moisture transport and thunderstorms there in the Sahel region of West Africa. You get massive complexes of thunderstorms, big lightning as well. And those are within the intertropical convergence zone. And when those blobs of thunderstorms move from West Africa from east to west and then move out over the tropical Atlantic, those surface temperatures are a lot warmer. And that leads to those blobs of thunderstorms associated with a tropical wave, or basically a storm system that moves from east to west across the tropics. When those thunderstorms continue to grow and you have favorable atmospheric conditions, sea surface temperatures greater than 80 degrees Fahrenheit, then they start to slowly spin because of the pressure that's falling near the surface with all that latent heat happening. And once you get that low pressure starting to form at the surface, you'll start to see that spin appear on satellite. And once you get organized spin, that's closed rotation, then you get what's called a tropical depression. And then your positive feedback starts to get out of control, and it can rapidly intensify into either a Category 5 hurricane or even a super typhoon.
Nice. Thank you. That's great to hear about the origins. I saw a bunch of people throwing in the chat there, like exact locations. That's like Cape Verde. A bunch of those kind of go through. So it's cool seeing everybody get involved on that. Hey, we've got one more live studio audience question for you from the Weather Wonders campers. Aiden, you are on with Reed. What's your question?
What's the largest storm you've been on the ground with?
Well, the largest tornado I've ever been on the ground with is the El Reno, Oklahoma tornado in 2013, May 31st. And that was the largest tornado in recorded history at over 2.5 miles wide, that tornado. So a very large tornado. The largest hurricane I've probably chased, and I would say probably Hurricane Katrina there in southeastern Louisiana. I chased that one in Slidell, Louisiana, saw a lot of that storm surge as well coming in. Superstorm Sandy was another very large storm that was transitioning into an extratropical cyclone. But definitely the largest tornado I've seen was the El Reno, Oklahoma, one at 2.5 miles wide. largest hurricane, I would say, is Hurricane Katrina. But just because a hurricane is large doesn't mean that it's more intense. In fact, like Hurricane Wilma that had that really compact eye, a relatively small compact eye wall, that was actually one of the strongest storms in history, even though the inner core of the hurricane was much larger than the pinhole eye within it. Great question.
Yeah, I agree. Thanks so much for that. It's just so cool hearing about your experience, Reed. And I think that's inspired a lot of folks. So I want to remind, I guess I told the campers maybe before class, but we'll remind everyone out here, Reed's coming back again in probably about 6 weeks or so with a class all about being a storm chaser. But I think one of the other big questions we get, so we're going to do a class all about it, but one of the most common questions we get. So maybe we'll end with this one here. We've got a whole bunch of kids out here who are fascinated by weather, sort of like you were when you were young, who want to learn more, who want to get close to storms, but still stay relatively safe. So what's your advice to to kids who are fascinated by weather? They need to stay safe. They'd love to be like you someday. And then maybe a little bit of a teaser for your How to Become a Storm Chaser class coming up in September. But what's your short-term advice for kids who are fascinated by weather?
Well, if you want to be a storm chaser, first of all, tuning into our next class would be a great step. I'll lay out a roadmap on how to become a storm chaser and a meteorologist and the importance of science in storm chasing as well. But right now at your ages, there's so much material out there to learn that's available. So many storm chasing videos. Varsity Tutors is an incredible resource for meteorology and for storm chasing, learning how to math behind meteorology, learning how to become a storm chaser in the next class as well. And there's a lot of content out there that's available. There's also National Weather Service offices that are located very near many of you in cities scattered across the country. There are internships available at National Weather Services. There are kids camps also available there where you can shadow a forecaster who's issuing all the watches and the warnings out there. But just ask questions, learn, watch as many videos as you can, read as well, read these Storm Prediction Center outlooks that are issued, read the weather watches that are issued as well. And then maybe one day down the road, you'll be able to storm chase safely as well. But this next class, I'm going to teach you how to do it safely and lay out a roadmap for anybody that's interested in becoming a storm chaser or a meteorologist.
That's fantastic. I'm really looking forward to it. I didn't mean for that question to be a sales pitch, but we get asked it all the time, which is why you and I decided, hey, let's just do a class on it coming up soon. So a lot there. And then I also think what you mentioned of just, there is a lot of great weather information out there. Follow Reed on social media. We're going to have his Instagram handle up here in just a second. And you get to see, I find you're better than, weather.com or the app on my phone. I kind of know what's going on all around the world just by following you on social. So there's all kinds of great weather information out there. I don't think we've ever been we've never been this good at predicting weather. And so, follow Reed and you'll find out kind of, not just what just happened, but what's coming up. And yeah, come back for more classes. We'll have Reed back here relatively soon. And so I guess with that, I want to thank you again, Reed, just for, such amazing weather enthusiasm and so much information and all of that went with it. So thanks to Reed. Thanks to all of you out there for whatever reason, when I don't know, there's thunderstorms, lightning, electric, there's some connection there, but when Reed's on, the chat is just electric with commentary and participation. So thanks to all of you for making this so fun. And like we mentioned, there's plenty of great information out on the on social media there. By following Reed to find out what storms and events are coming up next. It's also where you can put those tag those selfies to be entered to win a spot in Weather Wonders Camp. So I think we'll leave you with that. Thanks to all of you. Thanks, Reed, and we'll see everybody back here soon.